I understand why he can't be here right now. He started in August, so this is literally. Hence, me and then Christopher are going to present his work, but also the work of Patricia Glocke, who is a new PhD student in our lab. She started less than 4 weeks ago, 4 months ago. 4 weeks would be very short. And yeah, so what we're showing here is basically the new project we started earlier this year, and most of it is preliminary work. As you all know, urban heat islands exist. And about 75% of the urban population actually live in an urban heat island. It is a surface urban heat island in this case. And with increased urban temperatures, this is a great risk to heat-related morbidity and mortality. So we all care about urban heat. That's why we're at this conference. At the same time, 75% of the residential energy consumption in Europe is used for heating. So we have too much heat in the city, and at the same time, we need heat in cities because so far most of that heat is supplied through conventional, that means carbon-fueled methods. Both of these facts are connected through the shallow underground. We've done a study that simply showed that subsurface and surface urban heat islands do correlate. And we also know that we can basically recycle that heat in the underground or extract that heat in the underground through shallow geothermal energy systems. A ton of studies are done in this case, not so much by me, I must admit, by a lot of my colleagues, that basically look into how we can use ground source heat pumps or groundwater heat pumps to extract that energy. We got a really exciting grant earlier this year to kind of ask a little bit of a risky question. Can sustainable heat recycling in the subsurface help mitigate urban heat locally? Which is like a lot of works. This is how I sold it to kind of a funding agency, but in the end, we want to answer two questions. First is where and when can actually heat recycling help to fulfill our heating demands? So this would be figuring out where can we install systems, where it is financially feasible, where it's technically feasible, but also, and this is what we're going to talk today about, how are the atmospheric subsurface and the subsurface urban heat island connected? So which processes connect these two? And particularly, how is the surface urban heat island or the atmospheric urban heat island impacted by the underground? As a first step, we started with a sensitivity analysis. So the first goal was to just figure out, okay, what actually happens if temperatures in the subsurface change? What happens to the urban climate? And to do so, we modeled the urban climate with varying subsurface temperatures, or deep soil temperatures, as you would call it in this case. We've so far done 2 tests on this in the middle of the second one, and there's also a planned real-world domain scenario in Berlin. But today we're going to show an initial testing on an existing domain in Stuttgart and also some tests in an idealized domain. The tools for that is Palm4U, which is where I'm going to give you the talk, and I guess you can introduce yourself again.
Hello. So yes, hi. I'm Christopher Holst. I work mostly with Palm4U these days and also with observations, but I'm a meteorologist, so I'm more interested in the atmosphere usually. And this is where we work together, is that Susie is an expert on the underground and I'm sort of doing everything except the underground that's happening sort of in the atmosphere above. And I have used this relatively complex, as we have heard in many talks already, model that we have, Palm4U. And one important ingredient, of course, of Palm4U is the land surface model. I'm trying to find it on this list. It's on the right bottom of this schematic, as you see, because it actually simulates soil moisture and soil temperature and also things like roots and, processes related to plants, etc. So in principle, at least, with that model, we can address some of the question of how the atmosphere and the soil are linked together there. So we have talked about already observed data. Now, the problem is really that when we drive a model, usually we use some reanalysis data product like ERA5 or similar products from American reanalysis model. And usually they don't actually account for urban subsurface heat balance. When you look at the soil when you look at the soil temperature, or basically soil temperature proxy, you see that you have a relatively large difference in those two plots that you see there. And the difference is at the order of, the number is not written here, but it's at the order of several Kelvin, right? So the question is, how large would the effect of that error, of that, let's say, error at the bottom boundary of that model soil, how large would that effect be in the model atmosphere then? Can we quantify that? And it leads to a few interesting technical questions. That is, how would you even simulate that? Because when is the model actually in a steady state? Let's say, how do you initialize it? Like, which data can you choose? So in order to get a feeling for that, we devised a very simple test where we just took a domain. That's for those of you who have attended my talk yesterday, I've run a simulation on 20 by 20 kilometer domain in Stuttgart with 40 meter of grid spacing. It's a German city. And we have run it for 24 hours with a soil spin-up of only 24 hours, because we wanted to know, what if we would just extract a lot of heat from the deep soil and then let the model run and see what happens. So if you drop the deep soil temperature by 10 degrees, then you see that even after 24 hours of soil spin-up, you do see a relatively systematic decrease of atmospheric temperatures 10 meters above the ground, which in this case, it's at the median temperature is this like little orange line. And by median, I mean it's a terrain following kind of horizontal cross-section. And I've just taken all these grid points on that horizontal cross-section and bunched them into the statistics. And you see the difference there. It grows sort of linearly overnight in stable atmospheric conditions, and then up to a certain value of about 1 Kelvin in the median. And then in the daytime, when convection sets on, the offset gets a little bit smaller. But that's very interesting, because we're only talking about 24 hours time, basically, for a temperature offset signal to travel from the deep soil up to the surface and into the air, right? I mean, it's not obvious why it should do that, why it should happen that fast, actually. So when we actually ask this question, we want to know, okay, how do soil properties actually behave in that way? Like, which aspect of the soil is it that we are actually interested in there? So we tried this for a 2-month soil spin-up to sort of give the model a little bit of time to approach something like an equilibrium state. And with a relatively small domain and relatively simple radiative forcing, and just try to control as many variables as we could in a complex system like this, and just do, let's say, variation analysis on the deep soil temperature variation. And then what you can do is that you can calculate the same type of information from an analytical model. So it gives you an expected value. And you see that the amplitude you expect is somewhere around 8 Kelvin or so. This is what happens, but it only happens in the very, very shallow soil. So, and you also see that the soil depth at like about 1.75 meters into the soil doesn't really change much. Now, how does Palm do this? Because obviously the analytical model has different kinds of assumption. And let's see. So you can see that basically in the Palm model, if you change the deep soil temperature, you see that the effect is largest, of course, the lower you go into the soil, and the closer you get to the surface, the effect of the atmospheric forcing actually becomes larger. Now, in this case, the atmosphere is not actually, strictly speaking, driven by the soil temperature itself, but we fix the profile of the air temperature to a more or less constant value by imposing boundary conditions. Okay, so it's basically, we see this effect, which is basically caused by the forcing of the soil and the radiation balance at the surface. And for bare soil, you see that basically the diurnal amplitude of temperature change is relatively large. So meaning that the difference between morning temperature and let's say late afternoon temperature, when you have maximal forcing of radiation, is very large. When you, however, look at tall grass, which is another land surface type, you see that tall grass has a very substantially large effect on the insulation of the soil temperature behavior. And this becomes very interesting now because, as you have seen, we're talking about a difference of a factor 10 here with respect to temperature amplitudes, and then also with respect to how it actually behaves in terms of the vertical profile. So that raises interesting questions when you talk about horizontal gradients in a heterogeneous case, like in a city, right, where you have those two basically types sitting right next to each other, and maybe even more extreme types like very compact asphalt or concrete surfaces, which even have higher heat transmissibility than, let's say, bare soil in this case. So as we have said, this is very preliminary at the moment, and you see that the effect is fairly substantial. So it's a really interesting question because it raises other questions about the coupling between the atmospheric model and the soil, and how to even spin that up in a correct way, because they are supposed to inform each other, but it's like, how long do you want to run a simulation like that? Because it becomes at some point computationally expensive. So there's a lot of open questions still in this, and we are investigating more. So yeah, maybe, do you want to wrap up, or?
Okay, I can if you want.
Sure.
Okay, so basically, in summary, we started a new project that I'm excited about. That's trying to answer, if sustainable heat recycling in the subsurface would impact surface temperatures at all in any ways. And to do so, we need to answer two questions. First, where can we actually do sustainable heat recycling? And second, and this is the one where we're currently at, how are the atmospheric and the subsurface urban heat island connected, and how can we model this as well in models that are typically used in the atmospheric urban heat islands, or models that are typically used in the subsurface urban heat island, which we haven't done so yet. So first we did a sensitivity analysis in Palm4U. This means modeling urban climates that we keep stable, and then the only thing we change is basically the subsurface temperature. We did an initial test just based on an existing domain. This is the Stuttgart case he introduced. And then we changed the deep soil temperature quite drastically by minus 10 degrees Celsius. So this is way more than you expect to find, but basically for the beginning, if you have no clue what to do, you take 10 because it's a nice and round number. So we reduced it by 10 degrees Celsius, and we did find quite significant effects. So decreasing temperatures at a deep soil, as it is called in Palm, in reality it's like at 2-3 meters, cools this near surface air temperatures by up to 0.9 degrees Celsius. We are currently also testing it as an idealized domain, but so far this is unconclusive because, well, we haven't really figured our model out yet. This was primarily done last week, the testing, which next time we'll prepare more, and in 3 years you'll see like better results, hopefully. But what we can actually show by coincidence with our setup is literally the impact of land cover on subsurface temperature and how drastically these really impact subsurface temperature. This has also been studied before, so this is also kind of not an excitingly new finding, but as far as I know, it has never been modeled in Palm4U at least, or with an atmospheric modeling system. And yeah, we found that at 20 meter steps, there are really 10 degree Celsius difference in temperatures under tall grass or in temperatures under bare soil, which I find quite a bit at 10 p.m. is maybe I should also say this. And yeah, thank you very much. I think this was it.
Questions? Questions? Any questions?
Thank you. It's a great presentation. It's more of a comment. So
Yeah.
I've seen studies about different layers of soil temperature and moisture, and sometimes there is a seasonality of the gradient between shell and soil. And I'm just saying it could be very important for winter or spring.
Mm-hmm.
So yeah, I think it would be a good thing to include.
The question or the comment was about the seasonality of temperatures in the soil, which we do absolutely see, like down to approximately 20 meters, depending on where you are. Like it absolutely depends on the soil properties, on the thermal properties of the soil, but down to approximately 20 meters, we see seasonal variation in soil temperatures. This is with the phase shift, so the deeper you go, the later your shift is, and it's also dampened, so the deeper you go, the less seasonal variation you see. But the question was whether this is impacted here, and the answer is absolutely yes, it is. Right now, at the beginning, we basically model a world where seasonality doesn't exist in a sense of seasons for studying. What we're currently setting up is also a real-world scenario of Berlin, which of course has seasons. And here we are planning on just studying both winter and summer temperatures separately. Yeah.
Any more questions? Thank you very much.
Thank you.
Thank you.